you all for showing up, and hopefully this will be a bit of an interest to you. So to start with, the nice thing about astronomy and SPH and stuff like this is you get to make beautiful videos. So this is from my 2019 paper on star cluster formation. One of them has magnetic fields, one does not. And so what I'll discuss today is a bit of a crash course on the smooth particle hydrodynamics. So the first half of the lecture will give you a lot of the foundations, the rudimentary principles that go into this. So hopefully you have a good idea of what's going on by the end of that. And then this method has been built upon quite a bit by adding in a lot more physics throughout time. So in the second half of the lecture, then I'll give a very brief summary of some of the important aspects, including magnetic fields, dust, gravity, sync particles, and boundary conditions. Unfortunately, I'll really only get to touch on each of those aspects on a couple slides. So this SPH method is actually very, very versatile. It is used quite frequently in astrophysics, and it actually has an astrophysical origin. However, it is also very, very widely used in engineering aspects and also in video games and the entertainment industry. So if you've ever seen The Day After Tomorrow, that whole sequence where the tidal wave is coming into New York City was generated using SPH modeling. So this is a very prolific method. And it started back in the late 1970s with these two seminal papers, one by Lucy and the other by Gingold and Monahan. Oddly enough, both Lucy and Gingold are no longer in academia. Joe Monahan, however, is still very active, and I personally am lucky enough to have had the chance to know him and to work with him for a while. And so this method actually started back in the late 70s, where they wanted to model a star, and sorry, I forget the exact details with it. But since this astrophysical application, it has since progressed quite a bit. But it did start right here in astronomy. There has been a lot of very useful reviews over time, and Joe Monahan himself has written a couple one. And Daniel Price, this 2012 review, is one of the more recent ones and one of the ones that I typically reference quite a bit. There's a lot to it. It is a fairly dense paper, but it is a good one that I would recommend. If you're interested specifically in magnetic fields, a few years ago, I gave a talk on magnetic fields in SPH, and here's a link to the slides for that talk. That obviously goes into much more in-depth into magnetic fields than I'll be discussing here. So the first question that we have is, we have a region of space, and how do we divide it up numerically? So for this example, we have a dense sphere inside a low density medium. And intuitively, it's nice just to divide it up into a grid. And this is how a lot of the Eulerian methods, or how all the Eulerian methods work. You just put down a grid, most simply of fixed cell size, and then we can figure out at each given point what are the properties you care about. Now, this is not how SPH works. The nice fundamental property behind SPH is that it is supposedly meshless, which means we have no underlying grid. So what instead we want to do is we use a Lagrangian method, and rather than breaking this up into a grid which has cells of finite volume, we split it up into particles that have a specific mass. So what we want to do is take our region and replace it with a lot of little particles. And for stability, it is recommended that each particle has the exact same mass. And in most of the recent SPH codes, particles do have the same type of mass, or each particle does have the same mass. So if we have the same mass per particle, that means to represent a dense region, we just need more particles. So in this example, we can see we have this nice sphere where we have a lot more particles than in the background, which has a lot less density. So now, then the question is, where do we calculate the properties? Instead of calculating it on a grid, which we don't have, we can just calculate the properties we care about at each and every point or on each and every particle. So as a brief aside then, for those of you who will be developing your own codes, how do we initially place the particles? And just as a quick slide with this, we do have a lot of initial placements we can put them in. And most codes are developed in such a way that we can implement any of these methods just by flipping a switch. So you could put it on a nice regular lattice, or you could just essentially put them in a random position and hope that it matches the density. So an open question that I will not get into here is, does your initial conditions matter? So whether you have, say, a uniform density, or if you essentially condense it, doesn't matter how you place your initial particles. Again, that's something that I won't get into here. So going back to our grid, which here, for simplicity, we have set up on just a regular lattice. And density is arguably the most fundamental property in astrophysics and is definitely the most fundamental property in SPH. So the question is, how do we calculate that? In a grid, it's very simple. You have your cell of finite volume. You can just calculate the total mass in it, and you have density. But here we just have a bunch of individual particles. So this becomes a little bit more of a complex method. So what we do first of all is it's essentially a weighted sum. And density is quite simply calculated by this one, the equation on this page. So we take the sum over all your neighbor particles, which we'll define in a few moments, and multiply it by the mass and this function w, which is a smoothing function. And the smoothing function is the other fundamental aspect of the SPH method. And it is effectively a weighting function to figure out how far away you are, how much should you contribute to your density, for example. And I've just sketched out two different possible smoothing functions that we have here. So as you can see, if a particle is closer to the dot or to the center, then it should have a contribute more to the density or whatever other value you're looking at. If it's much further away, then it will contribute a lot less. So the question then is, what is W? What smoothing function should you have? And if you can see the two shapes that I put here, you should be able to guess that a very simple function is a Gaussian. And you just normalize it to be 1. So the sigma is a normalization factor. H is a scale parameter in this equation, where that dictates the width. So the two Gaussians that I've shown have different widths. If we look at this on just a 2D plot, we see a couple of different Gaussians. So that suddenly leaves H as being a free parameter. And whenever you're doing numerical methods, the fewer free parameters you have, the better and the more robust it is. So having H a free parameter is not something we're overly comfortable with. The other catch is, for Gaussian, W is always non-zero. So that means no matter how far away a particle is from you, it will have some non-zero contribution to your characteristics. Now, in numerical methods, that means we have to calculate an n-squared, and perform an n-squared calculation. And that gets both very, very expensive and somewhat pointless, because if your particle is really, really far away, it will contribute some, but it'll be a negligible amount. So what we really want is a function that is similar to a Gaussian, because the Gaussian does have a lot of the characteristics that are desirable, but we want something that goes to 0 after a certain distance. And this is known as compact support. So we actually have quite a few of these kernels that fit this description that are similar to Gaussian, but go to 0 after after a given distance. And the most commonly used one in astrophysics is known as the cubic spline, which is shown here in blue. And I've given the equation here. So this is actually a piecewise function, and it is dependent on, or the input parameter is essentially the ratio of the distance to the particle you care about and the smoothing length. And if it's between 0 and 1, we have this top line. If it's between 0 and 2, it's the middle line. And most importantly, if you're between or greater than 2 away, then it's 0. So now suddenly, rather than having to care about all the particles in your domain, we just have to care about the few that are within 2h of you. So this will make your methods a lot more efficient. So we've now realized how we can place our particles, and we now know that we want something, a smoothing length, a compact support kernel, rather than a Gaussian function. And the final question now that we get to look at is, what is h? What is, so for the Gaussian, that was just a free parameter. Now, we could arguably use a free parameter here as well. And for example, in this example, I've just drawn on a bunch of circles that represent values of constant h. And what we can see is if we're in the middle of the sphere and we use this value, we have a lot of particles within our neighbor, or within the 2h value. If we're in the middle of the background, like the top right part, or the top right example, we have very, very few particles within our 2h. And if we're near the border, we have somewhere in between. So is this a reasonable approximation? And the answer is no, because it's inefficient, because in some cases we have possibly hundreds or thousands of particles within your 2h, and while at the same time other particles may have 2 or 3. That also means the weighting of these particles will be very, very different. So despite having every particle having the same h, we don't actually have consistency amongst the particles. So fixed h is bad for SPH methods. And so the question then is, what do we do? If we don't want a fixed h, what is instead more reliable is if we could have set h as a variable such that we have, say, similar numbers within 2 smoothing lengths. And that's what's happened in this example. So the circles are different sizes depending on what they are, but in each case, we have very similar numbers of particles within each circle or sphere. We're looking at a 2D projection. So we can see that in the dense region, your sphere is much, much smaller. And in the background, it's much, much larger. And if we're using the cubic spline, and if we're in 3 dimensions, each circle has approximately 57 particles within its neighbors. So this is now a much more reasonable and reliable method. We now have every particle is weighted by approximately the same number of neighbors, and we don't have an excessively large number of particles around any given neighbor. So we have consistency and computational efficiency. But this does lead us to the question of how do we calculate the smoothing length then? And this is done by an iterative process. So the density is still the same function that we showed before. And the smoothing length is now given by the second equation. And you can see that they're both dependent on h and density. So this does need to be solved iteratively. ideally through the Newton-Raphson method. Yeah, so n is just or eta is a free parameter that is dependent on the particular smoothing kernel. And again, we have approximately 57 neighbors in 3 dimensions if your kernel is the cubic spline. Now, what this also means is we have a simple relation that if you have a high density or higher density, means you have a smaller smoothing length, and that also means you have higher numerical resolution. So arguably then, in the middle of the sphere, where we have the small circle, we actually have a much higher resolution, numerical resolution than out in the background, where we have the much larger smoothing length, so therefore a smaller resolution. In the majority of astrophysical cases, the regions of interest that we care about and are analyzing are typically those that have high density. So that means we automatically get higher resolution in these higher density regions that we care about. So that is one nice benefit of this SPH method. So that is a bit of a crash course on how we put down the particles and how we calculate the density. But as you know, in any fluid dynamic simulation, we have a lot more than just density that we have to worry about and care about. And so the next few slides will have a little bit more math on them, but hopefully it's a bit of a useful reference at the very least. So how do we calculate values that are other values at the points on the grid, or at the points in our domain? So if we have a variable a, we can write it as a nice integral, where d or delta is the delta function. So the top line is just your identity function, since this is 1 only at r prime and 0 everywhere else. If you replace your delta function with a smoothing kernel, then we get the second line, and we have higher order errors that we'll ignore. And now we can multiply through by row on row, because this the integral is over a volume element, and for SPH we want a mass element. So we get this mass element. Now we finally convert it into a summation, and we have an approximation for how to calculate the variable b, or the variable a, in SPH. So we can see that the particle of the mass of the particle is written right into all these equations. We care about the value of a of all of the neighbors, which is weighted by the density and the smoothing kernel. So quite nicely, this is how it's all calculated. Unfortunately, most things in the fluid dynamic equations are derivatives, and this leads to a little bit more complex calculations. So in theory, one would think we'll just take the derivative of a, which we do right down in the top line, and then, excuse me, you go through a little bit of math, and we have the second line. And the really nice thing about this is we never have to worry about the derivative of a sub b at all. So we only care about the actual properties of the neighbor itself. And it's the derivative of the smoothing kernel that we require. And the smoothing kernels are all nice analytical expressions. So we know exactly what the derivative is, and the derivative can be directly hard-coded into the code. Now, if you're looking at this, you might see a bit of an issue straight away. And that is, if a is a constant, then by definition, your derivative is 0. But that's not true with this expression. And that is not good. So this is one of the first complexities that we have to deal with in SPH. So how do we get around a non-zero numerical derivative when analytically it is? So what we can do is we can rewrite our derivative. So the grad of a, it can be rewritten as the following expression, where phi is just any parameter you want. So phi is just an arbitrary function in this particular case. Now, using the above expression, we can sub in for both parts and do some math and rearranging. And now what we have is a new derivative where if a and b are the same, this term goes to 0. So suddenly we now have a new expression where if your value of a is constant, so is the derivative. And now we have more or less recovered exactly what it is we need to recover for the numerics to match the analytics. And the question, right. So then the question is, what can phi be? And an obvious answer is just set it to 1, which gets you this top expression. However, since density is a fundamental property of SPH, we can also just set it to be the density, which we get in the bottom example. So now we have two different expressions for the first derivative. Both of them will yield a 0 numerical derivative when the analytic, or when a is constant. So I should mention that this is not a complete description, because the smoothing length, as I discussed a little bit earlier, does vary depending where you are in the grid. And so it does change with density. That also means it changes with time. So h, you actually have to account for the derivative of the smoothing length as well. And that requires a little bit more complex math that I'd rather not get into in this talk. But it is covered in quite a bit of detail in all the review papers I put at the beginning. So it just simply means, well, not simply, but it does mean when you account for a non-constant smoothing length, we do have some extra terms that we will have to account for. And I'll point those out on the next few slides. Okay, so now we also have a good idea of the math behind the SPH method. And if you have to develop some new equations to embed into the code, then, excuse me, it will be following a similar process to this. Okay, so now let's try and put this all together a little bit and see what we're dealing with. Now, in astrophysics, the majority of what we want to model is gas. And at least the fundamental aspect of what we typically want to model is gas. And that very nicely follows the fluid dynamic equations. So here we just have the simple hydrodynamic equations written in nice continuum form. And hopefully you have all seen these in your coursework to date. Now we need to discretize this into the SPH form that we can actually use in codes. And this looks a little bit messy, but it's hopefully not too bad. So what we have here is we're calculating everything at the position of particle A, so subscript A. And we can see it's depending on either the quantity properties at its own point or the properties at point of neighbor B. And we're summing over all possible neighbors, which ideally is about 57 particles. So for density, we see here we don't actually have a derivative that, rather than evolving density as per the hydrodynamic equations, we just recalculate it at every given step. So we're able to remove one derivative from this. And again, we see that this is a iterative process. Now we have the equation of motion, which is the velocity, or the pressure over your density squared times the gradient of your kernel. So this is, you will be weighted depending on how far away you are, and also on your own scaling length, on your own smoothing length. Now, due to symmetry, and if you work through the equations, we see we have the same term again, just against property the properties of particle B. And we have these big capital omega terms, and these are the correction terms to account for variable smoothing lengths. Typically, they're near zero, or correction, they're near 1. And so if you have a very smooth field, it's 1. It becomes further from 1 once you get to very steep shocks and very in regions where your density is changing very quickly. For the next, we have the energy equation. And we can see here that all the terms, the pressure, your correction term, and density have been pulled out front because they only depend on particle A. And we have it depending on, this is the difference between your two velocities, so just the velocity difference. And finally, we have an equation of state. And this one is slightly different because there is no derivative, as we would expect from the previous slide. But also there's no summation is required. This is just a straight, simple calculation of, in this case, the density of particle A times the energy of particle A, and you get the pressure at for particle A. So you do need a little bit of care as to whether you can just do a direct sum and avoid a derivative, whether you need to do the derivatives themselves, or it's just a simple calculation. Okay, so now if we were to code all this up, what happens? And hopefully we can run a nice little test and see what happens. So in fluid dynamics, the main test that people typically run is known as the solid shock tube. And even on all the small simulations, all the test programs you run this code just to make sure it works. And it's a very simple setup where you have no initial velocity, step in density, and then a corresponding step in energy and pressure. The black line is the analytical solution, and you'll see a whole bunch of dots that represent the values of the actual individual particles. And when we run this, we see it's not that good. Density doesn't look too bad, but you have a lot of ringing right at the edge. When you look at the velocity or the energy, you have even more ringing right at the edge, and a nice little pressure blip. Now, looking at this, you might instinctively think that we have some catastrophic problems, we should all pack up and go home. But first of all, you actually have similar problems if you use grid codes. And this is actually fairly well-known issues because we are, what we did on the previous slide is just a direct translation from the continuum equations to numerical, but we need to account for numerical issues that may arise. So what we actually need to do is add in terms that will account for these numerical effects. So we have the physical terms that we've already looked at, and now we need to add in artificial terms. And if we're just dealing with a pure hydro equation, we need 2 artificial terms. So artificial viscosity, which is a term that is very commonly used within numerical simulations. And this is a correction term to the momentum equation. So it affects your velocity. Sorry, to the equation of motion to affect the velocity. And we also need a correction to the energy equation, which is artificial conductivity. Now, there's no real set form of the equations. Most people have kind of converged on what artificial viscosity should look like, but there are still several different terms for artificial conductivity. But once we put that in, we can rerun the test. And now we see that everything looks very good. So all of our ringing is gone, our pressure blip is gone. We do have some smoothing issues right at the border, but given how by nature SPH typically smooths over shocks, this is not unexpected. If we were to run with higher resolutions, then we find that this gets, the shock front itself gets steeper and steeper, and we better match our resolution. So now that we put in these artificial terms, we basically have a very good working code, and we can very well reproduce this test code, this test case. So that is a bit of a whirlwind crash course on some of the fundamentals of SPH. So we've briefly looked at, you start out with your domain, how to discretize that, how to convert the continuum equations into discrete equations, again, cautioning that you need to be careful when you are using variable smoothing lengths, how to use the variable smoothing lengths, additional caution used for derivatives. As a sidebar, if you think the first derivatives can be challenging, there's been even more work and more difficulty figuring out how to model a second derivative. And caution about artificial terms. Now, this is a very rudimentary and very quick crash course of what we've done so far. But in all the simulations and all the analysis that we expect you guys will be running, we do have a lot more physics that we really do need to put on top of that. So for the rest of the talk, I'm just going to step through a lot of that somewhat quickly, just to get an idea of how we can safely build upon SPH and do more realistic modeling of astrophysical phenomena. So the first thing, real quick, is time steps. So we have your numerical or your spatial resolution, which is defined by your smoothing length and how many particles we discretize your domain into. And we also have to figure out how we can, how we have to resolve the time evolution. And we actually have many different time steps that are calculated at any given time and any given point, and we just take the smallest one. Now, the one that you'll most frequently see or understand is, this expression, which is a CFL, or Courant-Friedrich-Levy-like time step, which is dependent on your smoothing length and, in most cases, the sound speed. C is just a constant less than 1. So for smaller h, which is smaller smoothing lengths, you have higher densities, which means shorter time steps. So this is just something that you do need to be aware of if you start modeling really dense regions. We have two methods of calculating time steps. Global, which is very simple, but somewhat slow because you're evolving every particle on the exact same time step. And then we have individual time stepping, where it's much more efficient because each particle is essentially evolved on its own time step. So stuff in the background that's evolving really, really slow, you only have to update once every 8 or 16, 32, 100 time steps compared to something in the really dense regions. In most codes, this stuff is robustly set up, so it's just a matter of choosing which one you want and turning it off or on. Now, one of the areas where you really do need to be concerned about time stepping is if you're modeling the formation of a star. And as we've done, or as I showed you in the video at the very beginning, if we have a star cluster, for example, it will, well, by design, form stars. And in a star, you're getting really, really high densities, which means really, really small time steps. And that just makes these things prohibitively expensive to run. And arguably, we would not be able to run the video or produce the simulation that we already showed you. So what we can do is use this interesting invention called a sinc particle. So what we can do is you take your dense region of space and basically get rid of it and put in a sinc particle. And these were first defined by Matthew Bate, Ian Bennell, and not Daniel Price, coincidentally enough. So these all, in this case, this represents a star. In some bigger simulations, you may have a sinc particle that represents an entire star cluster. So you do have to be cautious with these things. They are parameterized in the sense that we fix their radius. So that's just an input parameter. So the radius never changes. They can accrete gas. So if gas falls within their radius, it gets removed from the simulation and the mass of your particle increases. So if you watch the sinc mass, it should go up with time. One of the possible caveats or difficulties is sinks only feel gravity. They only have the gravitational forces. They feel it between the gas and other sinks, but that means there is no pressure forces. And if you're dealing with magnetic fields, there are no magnetic forces. Now, this could lead into some other issues, so you just have to be very careful and aware of what's going on when you're modeling and using sink particles. And here's a nice graphical description of what's going on at the bottom. So here we have two simulations taken at the same time. And the black particles in the back, I've just run the simulation as is. And for the red particles, we hit a certain point, and then I input the sink particle. So we can see that we get rid of pretty much every particle that has a density of greater than 10 to the minus 12 grams per cubic centimeter. And a giant sink particle, in this case with a radius of almost 7 AU to put in. So not only have we lost all the dense particles, but we do have a bit of a smearing out of density at this inner edge. So we are losing a reasonable amount of information, but it is a necessary evil if you want to model the long-term evolution of stars. So it's not bad, it's just something you really do need to be aware of if you're using sink particles. Another big aspect you want to look at is gravity. This is generally used in astrophysical simulations. You'd be surprised how often, though, people can actually avoid it and ignore it. Yeah, I think that slide was supposed to be deleted. Sorry. So quite simply, it's just put in with Poisson's equation, but solving Poisson's equation is unfortunately non-trivial. So what we can do is, you all know that gravity is just like a 1 over r squared calculation. So we take a point and we can calculate gravity by just calculating over every other particle in your simulation. Because gravity is long-range force, this has to be an n squared calculation. But we can be smart about it and use something called a tree. So what these codes typically do, there's different methods of doing it, but one of the methods is you take all your particles and you start breaking it up into cells, or in this terminology, leaves. And you keep breaking them up until each leaf only has about 10 particles in it. And then once you have this tree with all the different leaves, then we can use that to calculate gravity. And we split gravity up into two things. So first of all, we have short-range forces. So if we have a particle at one of these points, then we find out every cell that is within two smoothing lengths of it, and we'll do a direct n squared summation over all of those particles. Hopefully it's only a few hundred, so it's not too expensive. If we're within 2h, then we'll want to use softened gravity. Because as you know, since it's a 1 over r squared calculation, if you have two particles very close to each other, you can get a very, very high acceleration, which is not physical. So if we're within 2h, we have a softened gravity. If we're still in the cell that we're calculating with, but outside of that, then we just use a straight up 1 over r squared calculation. So now we know what the short range gravitational force is close to us. Now for the rest of the domain, we use long range forces. And what we do is we basically group these different leaves. And then we'll take each group and treat it essentially as a single point. So if we treat these 5 or these 4 cells as 1 point, then we're doing a one calculation, one calculation, as opposed to having to do quite a few. And especially considering if it's really far away, all these values will be very, very similar. So it's just kind of pointless to do the extra calculations. Now, how we group these cells will depend on their distance from the particle that you care about, and how big the cell itself is. If you're using gravity and interested in this, I can discuss this in a little bit more detail offline. But as a brief summary, we can see here that we have how we have broken down the gravity, where everything in your red circle is calculated using smoothed gravity, or sorry, softened gravity. Everything in this blue square, we still do a 1 over n squared calculation, but it is just the 1 over r squared gravity. And for each of the yellow boxes, we basically calculate the distance to the center of mass and the total mass of the box and use that as a single calculation. So for all these green boxes, it's one calculation each, which makes things very, very efficient. Now, since gravity and sinks, or since sync particles feel only gravity, we do have to treat them a little bit differently. For a lot of the codes that we use, we end up just doing basically an n squared calculation when it comes to the sinks. So for each sync particle, it's typically just n sync squared plus n gas times n sync calculations. As long as you only have maybe a few hundred sinks, this is really not too expensive, but it is, again, something to consider. I am running a little slower than I had hoped, but if you just bear with me, I guess I've still got a few minutes, so we'll just carry on. Again, this is a bit of a crash course and talk's designed to at least introduce you to the different aspects of an SPH code. So the next big aspect, and one of my personal fields of research, is magnetic fields. And so here we have the continuum equations again, and we've introduced a new term to your equation of motion and the induction equation. Now, we've actually done a lot of tests, and at one point we found that if we rewrite your induction equation to actually evolve beyond rho, it's more stable. So you see about both ways, but a lot of the numerical codes we use and a lot of the SPH codes evolve the magnetic field divided by density as the variable, as opposed to the magnetic field itself. Yeah, we have a lot of more math. This is hopefully just more a useful reference slide. Calculations do get a little bit more complex when we put in the magnetic fields. So again, that only affects really the equation of motion and your induction equation. Now, with magnetic fields, there are some inherent difficulties with this. So again, we require artificial resistivity, and I've done a study back in 2017 comparing different types. I think we've reached a consensus on the optimal type of artificial resistivity to include. Now, the main catch with this is, as you know from Maxwell's equations, div B is 0. Magnetic monopoles just simply do not exist. But if you go through the math on this slide and actually break things up into their individual terms, you can see that we get a numerical term that has div B in it, and due to how rounding, machine precision, and other terms work, that will be non-zero. So our equations will not get us a non-zero div B, and that can and will lead to a lot of difficulties. So what has been done is this whole new term and this whole new concept of divergence cleaning has been introduced, where we basically take a step, calculate all your magnetic fields, you calculate the divergence, and then we can clean it out. This was actually the topic of Terry Trico's PhD thesis, so there are quite a bit of complexities to it. Now, one thing we want to always track, and if you're evolving a magnetic simulation, you always need to be aware of this diagnosis term which is the smoothing length times the derivative or times the divergence of B on over the magnetic field. And you need to keep an eye on that. And as long as the average value stays low, so about 0.01 or smaller, and as long as the maximum value does not get too high, then your simulation is stable and reasonable. For the most part, this seems to work well. However, last year we came across a few simulations where this term can get really, really high and basically blow up and destroy your simulation. So we have come up with a bit more of a patch to try and control this. So again, if you're dealing with magnetic fields, always keep an eye on that variable. And as long as it stays small, you're fine. If it becomes too big, then you do need to look into fixing that. Now, a lot of astrophysics, especially in the dealing with young stars, exoplanets, protoplanetary disks, there's dust in there. And a lot of research lately has been trying to model and understand dust. So a lot of our codes can also now include and model dust. There's two ways to do this. Now, if we are modeling large dust grains, then what we can do is actually create two sets of particles. So we have one particle that represents just pure gas, and then another set of particles that represents pure dust. And dust is generally, or is a pressureless fluid, so we can ignore all the pressure terms with that. So it accounts for gravity amongst itself and between dust, or between dust and gas. And we also have these drag terms that couple the dust and the gas. So here we see we have two density equations, one for gas, one for dust. And we have two momentum equations, one for gas, one for dust. We have the drag terms that couple them, only gas has your pressure term, and so forth. And here's just an example of how 6 different grain size work within this formalism. But if we're dealing with really small dust grains, then things should be much more coupled, and we can actually use what's known as one fluid dust. And in this case, we have just one set of particles, but it represents both dust and gas. So we only have the one density equation, but we have this equation that involves epsilon, where epsilon is actually your dust fraction. So we can see that, so if we look at your velocity equation, we have 1 minus epsilon times whatever forces are affected by gas only, plus your epsilon, your dust fraction, times whatever forces are dealt by dust only. And then F is probably gravity or whatever is affected by both equally. And you also need to evolve the difference between your dust and gas velocities within each individual particle. So we do have these two dust formalisms. Both work very well. Both are designed to work in different regimes. So depending on what you want to model is depending on which one of these you'll want to use. If you're including sink particles, dust particles and these hybrid particles can be accreted onto the sink. Now, the last thing I want to touch upon is boundary conditions. So when you were looking at that grid back in the very beginning, we saw that you have a very well-defined boundary, and you have to do a lot of annoying or complex decisions as to what to do at those boundaries. In Smoothed Particle Hydrodynamics, we can actually ignore boundary conditions completely if we choose. So if we have just a sphere, or we're modeling a hydrodynamic cloud, which Matthew Bate has done consistently over the past 2 decades or so, or trying to merge 2 galaxies, we can completely avoid boundary conditions if we want. So the particles just go wherever they so choose. You will need to set up your initial domain. So we are in, so to encourage the particles to not just fly off to infinity. So that is one really nice aspect of SPH. If you are dealing with magnetic fields, this does not work. If you're dealing with magnetic fields, that would mean you just have an open magnetic field line somewhere, and that will cause havoc through your simulation. So boundaries are absolutely necessary if you are modeling magnetic fields. One of the simplest things that we found, and I've consistently used and promote, is to use the sphere and box setup. So in this case, I only care about this dense sphere, but I put in this low density background, and then I can thread the entire domain with magnetic fields. And then on the boundaries, we set up periodic boundaries, which are relatively simple to deal with. So we no longer have an open magnetic field line, so we're satisfying physics and not causing numerical havoc. It also is a much simpler boundary condition to use. So this is one of the better methods to use if you need to model magnetic fields. If you're not using modeling magnetic fields, then it should be safe to just ignore the background completely. So I think we have more or less reached the end of this crash course. So artificial terms are required. If you're modeling magnetic fields, you require a third one for the MHD. As far as I'm aware, we don't actually have an artificial term if you're modeling dust. I think the continuum equations properly do translate to the discrete ones with that. There are other caveats you have to deal with, but an artificial term I don't think is one of them. And with how SPH is written, we can so easily add in a lot of additional physics. And I've just touched upon briefly gravity, sync particles, magnetic fields, and dust. But there's so much more that can be put in there if it's necessary for your own research. And I'll just leave you with some coding words of wisdom. The big one that you can never underestimate is just always comment your code. You think you won't forget, but trust me, you will. This is from experience and from hearing other people say literally the exact same thing. And another big hint is never ever hard code stuff in. At the top of any given file, always list your parameters as variables at the top and define it there, and then just use it throughout. That will save you time. It's also a good coding practice to get into. So with that, I shall end my crash course on SPH. And